Welcome to week 11, question 8. We have what is called a Cobb-Douglas production function, and this production function relates units of labor with units of capital to determine production costs. So it says that X is the number of units of labor, Y is the number of units of capital required to produce N units of the product. And it says, this is important information, each unit of labor costs $8, each unit of capital costs $12. So once again, we're going to be looking at how to maximize production, and we have some constraint here about the costs. We have, again, in A, we have $80,000 is budgeted. So that's going to be our constraint, and we're going to combine these two functions using the Lagrange multiplier, Lagrange function, and we're going to solve for x and y. So the first thing we need to do is set up our constraint function. So it would be 8x plus 12y is equal to 80,000 because that's how much money is budgeted. And remember, we need to have this equation equal to 0, so we've got 8x plus 12y minus 80,000 is equal to 0. So we're going to set that aside, and we're going to set up the Lagrange function, and remember that is the original function minus lambda times the constraint function. So let's set that up. From here, you're going to want to expand these brackets. Remember, applying that negative lambda over each of the terms. So we'll do that next. So we have minus 8 lambda x minus 12 lambda y plus 80,000 lambda. Okay, so now we have three variables. We need to take the first derivatives, partial derivatives with respect to each of those variables. So we'll start with f sub x of xy lambda, and we have, let's see, 80 times 0.7 here is 56x to the negative 0.3. That's using our power rule, y to the 0.3, and then we just have minus 8 lambda, because here that's those are considered constants in this case. Okay. Then we have the first derivative with respect to y of xy lambda. And so we have 80 times 0.3 in this case, because that's the exponent of y. So that's going to be 24 x to the 0.7 y to the negative 0.7, because that's 0.3 minus 1. And then we have minus 12 lambda. The negative 8 lambda x is a constant in this case, and so is the 80,000 lambda. So now the derivative with respect to lambda of xy lambda is simply negative 8x negative 12y plus 80,000. Okay, let's see what we do next. I've written both the partial derivatives with respect to x and with respect to y here. So we're going to set this equal to 0. And I'm going to want to divide that equation by 8 just to have lambda by itself here. So it'll be 0 is equal to 7x to the negative 0.3 y to the 0.3 minus lambda. And then we can say lambda is equal to 7x to the negative 0.3 y to the 0.3. And I'm going to look at this partial derivative here with respect to y, and I see that we can divide by 12, this one. First we'll set it equal to 0. And we should have something a little bit easier to manage. Lambda is equal to 2x to the 0.7, y to the negative 0.7. Okay, so now we have two equations that are both equal to lambda, and if we set them equal to each other, we should be able to find values of x and y. So we have 7x to the negative 0.3 y positive 0.3 is equal to 2x to the 0.7 y to the negative 0.7. Okay, so now we have to remember way back our rules of exponents. So you'll remember that if we are dividing exponents or multiplying exponents with the same base, so if we have, if we're multiplying exponents with the same base, we can add the exponents. If we are dividing exponents that have the same base, we can subtract the exponents. So that's something that we're probably going to be using here. And I'll go to the next page where we have a little bit more room. I've written the equation here again from the last page where we left off, and also our power rule note that we probably should have available to us. There's one more thing, and that is that ability to take negative exponents and put them in the denominator. So remember, if you have say 1 over x squared, that is equivalent to x to the negative 2, right? And if we look at our equation, 7x to the negative 0.3 y to the 0.3 equals 2x to the 0.7 y to the negative 0.7, you can see that we have both positive and negative exponents. And we can put the negative exponents into the denominator. So let's do that. Okay, so when we get to this stage, we're still trying to get x and y together. We're gathering these like terms. At this point, I would cross multiply. Remember how we can do that? In order to get all of our terms together. So if we do that, we have 7 y to the 0.3 y to the 0.7, so we're multiplying those together, equals 2x to the 0.7 and x to the 0.3. Now is when we need to be aware of our power rules. We have two powers multiplied together having the same base, so we can add the exponents. So y to the 0.3 times y to the 0.7 would just be y. because 0.7 and 0.3 equals 1. So we have 7y. And on the other side we have 2, and then again we have x to the 0.7, x to the 0.3, powers with the same base. We add the exponents, and so there we have just 2x. So if we isolate for x, you could also isolate for y. We have x equals 7/2 y. Now we substitute 7/2 y into our constraint, and I'm going to remind you that our constraint was 8x plus 12y equals 80,000. Right? That came from our original equation, our original information with units of capital, units of labor. Oh, got my y in there. So 8 times 7/2 y, just replacing the x by 7/2 y, plus 12y equals 80,000. So this we can reduce there. We have 28y plus 12y is equal to 80,000. So 40y is equal to 80,000. Y must be then equal to 2,000. Now we substitute y is 2,000 back into here to find our value of x. And we'll do that on the next page. Brought forward from the last page, we have x is equal to 7/2 y. We found that y was 2,000, so now we're just substituting that in. So that would be 1,000, dividing that out. So now we have x is equal to 7,000, and y is equal to 2,000. So our next step, or last step, is to substitute values of x and y into your production function to find out what the maximum production is at those levels. If you recall, our production function, our Cobb-Douglas function, was n of xy is equal to 80x to the 0.7, y to the 0.3, where x is representing units of labor, y representing units of capital. So now we have values of x and y of 7,000 and 2,000, so now we substitute and solve. You need to remember your order of operations rules. You're going to be doing the exponents first and then the multiplication. And when we do that, we find that we have a value of $384,563.10. So again, that's with 7,000 units of labor and 2,000 units of capital. That would be your production level.